A single photograph just captured 10 million galaxies in one frame, not with a space telescope orbiting hundreds of miles above Earth, but with a camera sitting on a mountaintop built by human hands, pointed straight up at the night sky. And that one image represents a tiny fraction of what this machine is about to do over the next 10 years. If a number like that doesn't stop you in your tracks, stay with me, because what scientists just unveiled is going to reshape how we understand the universe around us. And I want you here for every single discovery that comes out of it. For years, when people pictured groundbreaking astronomy, they pictured the James Webb Space Telescope floating in the vacuum of space, capturing pin-sharp images of galaxies billions of light years away. But something happened recently here on the ground that deserves just as much attention. A newly finished observatory in the mountains of Chile has started producing images that rival anything humanity has ever captured. And it's doing it in a way no other instrument on Earth ever has before. This is the Vera C Rubin Observatory, built at the summit of Cerro Pachon, high in Chile's Atacama region. In June of 2025, the observatory released its very first public images, captured using the largest digital camera ever constructed. Having followed the progress of this project for years, I can say with total confidence that what these first images show is nothing short of extraordinary. Let's start with the machine itself, because the raw numbers involved are almost impossible to picture without some real comparisons. The camera sitting at the heart of this observatory is roughly the size of a small car. It weighs close to 3,000 kilograms. Every single photograph it takes is built from over 3,200 megapixels, meaning each image contains more than 3 billion individual pixels of information. To put that into perspective, you would need somewhere around 400 modern televisions arranged side by side just to display one of these images at its true full resolution. That's not an exaggeration. One single photograph, 400 screens. And this camera doesn't just take a picture and stop there. In a single night of operation, it can generate close to 20 terabytes of raw data. Because the observatory itself sits in Chile, while the primary data processing facility is located thousands of miles away in the United States, engineers had to construct an entirely dedicated high-speed data connection just to move this information from the mountaintop down to Florida, where it can be processed and distributed out to researchers scattered across the globe. So what exactly do these images actually reveal? How does a machine like this even work? And what are scientists hoping to learn from a survey running across an entire decade? Let's get into all of it. Before we look at the pictures themselves, it helps to understand who this observatory is named after and why that name matters. Back in the 1960s, at a time when women were almost entirely absent from professional astronomy, Dr. Vera Rubin produced the very first compelling observational evidence that dark matter actually exists, all while simultaneously raising a family alongside her. Scientific career? It feels fitting that an observatory built specifically to hunt for the invisible architecture of the universe now carries the name of the scientist whose research first proved that architecture was real. Now here's something that might surprise you if you're used to hearing about telescopes like Hubble or Webb. Space-based telescopes produce such clean, sharp images largely. Because of location, floating above Earth's atmosphere means avoiding atmospheric blur and the glow of light pollution that ground-based telescopes constantly fight against. So why build something this ambitious right here on the surface of the planet? The answer, again, comes down to location. Cerro Pachon sits inside Chile's Atacama Desert region, one of the driest, darkest, clearest stretches of sky anywhere on the planet. The air there is so thin and stable that it provides some of the best observing conditions on Earth. It's no coincidence this same mountain range already hosts other major observatories, including the Southern Astrophysical Research Telescope, the Gemini South Observatory, and the Giant Magellan Telescope, currently under construction close by. This stretch of desert has proven itself again and again as one of the finest places on the planet to point an instrument at the sky. One more detail worth knowing before we dive into the images themselves. This observatory isn't operated by an agency like NASA or the European Space Agency. It's jointly funded by the United States National Science Foundation and the Department of Energy, and managed through a research consortium known as the Association of Universities for Research in Astronomy. A very different institutional structure than most people expect for a project of this scale. Inside the observatory sits what's officially called the Simony Survey Telescope, which, upon completion, became one of the largest telescopes anywhere in the world. Its primary mirror stretches 8.4 meters across, paired with a smaller 3.4 meter secondary mirror. But raw mirror size isn't really the most remarkable part of this design. What makes it genuinely unusual is a third mirror, roughly 5 meters across. Most telescopes rely on a simple 2-mirror configuration to focus incoming light and correct for the natural distortion that comes from curved surfaces. This telescope uses 3, which gives it an unusually wide, unusually sharp field of view across an enormous section of sky simultaneously. Attached to the far end of that telescope sits the camera itself, and this is genuinely where things start breaking records. It measures about 3 meters long and 1.5 meters wide, and it's built to capture ultraviolet, visible, and near-infrared light. Using a robotic filter changing mechanism to swap different lenses in front of its sensors, depending on exactly which wavelength of light it needs to isolate. This camera carries the official name of the survey it supports, the Legacy Survey of Space and Time, usually shortened simply to LSST. Inside, the camera is built from over 180 individual sensors, paired with 3 enormous lenses crafted from fused silica glass. Each single exposure captures nearly 10 square degrees of sky at once, which sounds abstract until you realize that translates into an area roughly equal to 40 full moons placed side by side in a single shot. That's an extraordinarily wide field of view for an instrument built with this level of optical precision. To really understand how significant that is, compare it against a previous major sky survey, the Sloan Digital Sky Survey. Across its entire 20-year run, that survey mapped roughly a third of the visible sky. This new camera, by comparison, can cover the entire visible sky of the southern hemisphere, essentially half the observable universe from Earth, in a single 3-day observing cycle. Put another way, roughly every 3 days, this camera accomplishes something close to what took an earlier generation of astronomers 2 full decades to build. And the 10-year length of this particular survey isn't really about needing that much time just to cover more area of sky. It's about something far more interesting than that. It's about mapping the universe across time itself, essentially building a searchable, ultra-high resolution time-lapse recording of the entire night sky, tracking how it changes night after night, year after year, in a way nothing before it has ever accomplished. Like most large sky surveys, this project is designed broadly to look for essentially everything visible up there, but it does carry 4 specific scientific goals driving its design. First, investigating the true nature of dark matter and dark energy, the mysterious, invisible components that make up the overwhelming majority of everything in the universe. Second, cataloging objects within our own solar system, things like asteroids and comets that have never been formally recorded. Third, monitoring transient events, sudden or short-lived phenomena like exploding stars, variable stars, and gamma-ray bursts. Fourth, mapping the structure of our own Milky Way galaxy in dramatically greater detail than has ever existed before. Earlier surveys laid important groundwork for this kind of large-scale mapping effort, but this new observatory is expected to push things dramatically further. Researchers anticipate that data from this single survey will help identify millions of previously undiscovered asteroids, expanding our current catalog on a scale that has simply never happened before. The good news is that you won't have to wait the full 10 years to actually see meaningful results. The team running this survey plans to release new images and findings continuously throughout the entire project, letting the public follow along in close to real time as fresh discoveries roll in. And as mentioned, the very first batch of these images arrived in June of 2025, and they absolutely did not disappoint. After just over 10 hours of initial test observations, this observatory had already captured cosmic activity on a scale that's genuinely difficult to process. Millions of stars and galaxies, thousands of asteroids, and all of that was only a small preview compared to what's still coming across the next decade. One of the very first images released has already earned a nickname among astronomers, the Cosmic Treasure Chest. Built from over 1,000 individual exposures gathered across 7 separate nights, it shows a section of the southern Virgo cluster, roughly 55 million light-years away from us, the closest large cluster of galaxies to our own. This single mosaic covers 25 square degrees of sky and reveals an almost overwhelming variety of stars and galaxies packed into one continuous frame. It's constructed by layering multiple exposures of the exact same patch of sky, taken at different times and through different filters, in order to reveal faint details that any single exposure alone would completely miss. Look closely near the upper corner of that image and you'll find 2 enormous spiral galaxies dominating the frame, with a trio of smaller galaxies actively merging just above them, thin threads of stellar material stretched between them like glowing filaments. Scattered around that central scene sit both nearby and distant galaxy groupings, along with a handful of stray foreground stars belonging to our own Milky Way. On the opposite side of that image sits a region nicknamed Cosmic Drama, where bright stars from our own galaxy shine sharply in the foreground, while dozens of nearby galaxies sit visible in the middle distance, and a dense speckled backdrop of faint reddish galaxies fills everything behind them. This single image alone is estimated to contain around 10 million galaxies. And remember, that number represents only a tiny fraction of the roughly 20 billion galaxies this observatory expects to observe across its entire 10-year survey. Another early release shows an equally striking mosaic of 2 nebulae, built from hundreds of individual exposures gathered across roughly 7 hours of observing time. In any single exposure, the faint dust and gas clouds that make up a nebula can appear almost invisible. But by stacking hundreds of exposures together, that faint structure suddenly becomes vividly clear. At the center of this particular mosaic sits the Lagoon Nebula, roughly 5,200 light-years from Earth. This pink, kidney bean-shaped cloud is one of the very few star-forming nebulae faintly visible to the naked eye from mid-northern latitudes. If you were to actually look at it through a basic telescope or a pair of binoculars, you'd mostly just see a faint gray smudge, because the human eye simply cannot detect the full range of wavelengths this observatory's camera is built to capture. Those extra wavelengths get translated into visible colors within the final processed image. Infrared light, typically associated with cooler material, gets mapped toward red, while ultraviolet light, associated with hotter material, gets mapped toward blue. For comparison, there's an existing optical image of this same Lagoon Nebula captured by NASA's Hubble Space Telescope years ago. That earlier Hubble image is genuinely rich in fine detail and also uses added color to represent information otherwise invisible to the human eye. But you'll notice that image is extremely tightly zoomed in, covering only a handful of light years across. This new observatory, by contrast, captures a vastly wider view of the exact same nebula, and the difference in scale is honestly startling. The Lagoon Nebula itself spans roughly 55 light-years across and 20 light-years tall, and yet in this new mosaic, it only occupies a small fraction of the total frame. Why is the difference in scale so massive between these two instruments? Hubble was designed specifically to focus tightly on individual objects, with its 2.4-meter primary mirror producing highly detailed images of very specific targets. This new observatory's 8.4-meter primary mirror, paired with its enormous 3,200 megapixel camera, was built instead to photograph huge sections of sky all at once, while still maintaining exceptional detail throughout the entire frame. Hubble's field of view in a single image covers roughly 1% of the Moon's visible surface area. This new observatory's field of view covers an area equal to around 40 times the Moon's surface area in a single exposure. That works out to roughly 4,000 times more sky captured per image compared to Hubble. That difference in scale is really the defining feature of this entire project. Looking again at that same nebula mosaic, the wide field of view reveals far more than just the Lagoon Nebula alone. Near the top of the frame sits a cluster of blue-tinted stars, an open star cluster, catalogued as Messier 21. Just below that glows the pink and blue haze of the Trifid Nebula, sitting roughly 9,000 light-years away in the constellation Sagittarius, occasionally visible, even through smaller amateur telescopes. Below that sits another open star cluster, and toward the bottom center of the mosaic sits a tightly packed globular cluster containing tens of thousands of stars. The sheer density of objects visible across these images is genuinely staggering, and it's worth remembering that even a rich, detailed cluster like that globular cluster amounts to little more than a tiny speck within the much larger mosaic surrounding it. But this observatory isn't simply producing beautiful pictures for the sake of it. It's already generating real, usable scientific results. In roughly those same 10 hours of initial test observation, it identified more than 2,000 previously unknown asteroids within our own solar system, including several near-Earth asteroids, none of which pose any danger to us whatsoever. For comparison, roughly 20,000 new asteroids get identified globally each year through the combined efforts of every other ground and space-based observatory currently operating. This single observatory is expected to discover millions of new asteroids within its first 2 years of full operation. It may also become our single best tool yet for spotting rare interstellar visitors passing briefly through our solar system, similar to the famous objects Oumuamua and 2I Borisov. Astronomers estimate objects like these pass through our inner solar system roughly once a year, but survey telescopes capable of catching them in the act are still a fairly recent development. That's not everything it found in those initial hours either. The observatory also detected dozens of subtly pulsating stars known as RR Lyrae stars, an ancient type of star commonly used by astronomers to measure vast cosmic distances. Over the full course of the survey, it's expected to identify up to 100,000 more of these stars, some potentially located more than 1 million light-years from Earth. Finding stars like these will help astronomers map the outer structure of our own Milky Way galaxy in far more detail than has previously ever been possible. In its first full year, this observatory is expected to collect more optical astronomical data than every previous observatory in human history combined. By the time the full 10-year survey wraps up, it's projected to generate around 500 petabytes of data. That's 500,000 terabytes, containing billions of cataloged objects and trillions of individual measurements, an absolutely enormous resource for researchers to work through for decades to come. Once full operations are underway, this observatory will repeatedly scan the entire southern sky, capturing fleeting cosmic events in close to real time, while building out that decade-long time-lapse record of the universe we mentioned earlier. It's worth appreciating just how long this project has been in the making, because it puts the achievement into real perspective. Serious planning and design work stretches back roughly 2.5 decades. Hundreds of scientists and engineers across multiple countries contributed to designing and building the telescope, the camera, and the massive computing infrastructure required to process everything it captures. The camera itself was assembled at a national laboratory in the United States before being carefully transported to Chile and installed onto the telescope during the early months of 2025. For a project this technically ambitious, the fact that it went from installation to producing genuinely spectacular first images within just a few short months is itself a remarkable engineering achievement. The public unveiling of these first images happened during a live event shared simultaneously with audiences and research institutions around the entire world. It marked the official symbolic beginning of the 10-year survey, even though full nightly operations were still being finalized in the months that followed. Let's talk a little more about why dark matter and dark energy sit right at the very center of this project's mission, because it's easy to hear those terms tossed around without really grasping how strange they actually are. Based on everything astronomers currently understand, the ordinary matter that makes up stars, planets, and every single visible object in the universe, including us, accounts for only a small slice of everything that actually exists. The vast majority of the universe's total mass appears to come from dark matter, an invisible form of matter that doesn't emit, reflect, or absorb light at all, and can currently only be detected indirectly through its gravitational effects on the things we actually can see. Layered on top of that sits dark energy, an even stranger force believed to be responsible for the accelerating expansion of the entire universe. Together, these two components make up roughly 95% of everything that exists, while the ordinary matter we can actually observe makes up only a small remainder. By repeatedly imaging billions of galaxies across 10 full years and tracking incredibly subtle patterns in how their light bends and how they're distributed across the sky, researchers hope this survey will help reveal far more about how these invisible components actually behave. One of the more genuinely exciting technical capabilities built into this entire system is speed. Because the observatory scans such enormous sections of sky so rapidly and so repeatedly, its processing system is designed to detect changes between one image and the next almost immediately, flagging anything unusual, a newly appearing object, a sudden brightening, something that's clearly moved position, and issuing an alert out to the global astronomical community within about a minute of the original image being captured. That kind of rapid, automated alert system means that if something genuinely new or unexpected shows up anywhere across the entire visible southern sky, researchers around the world can be notified and start pointing other telescopes at it almost immediately, rather than potentially missing a brief, fast-fading event entirely. If you want to explore these early images yourself in far more detail than any single video could show, the observatory has made an interactive online viewer publicly available, letting anyone zoom directly into these massive mosaics and explore individual galaxies, star clusters, and nebulae at their own pace. It's genuinely one of the more mesmerizing ways to spend 20 minutes if you enjoy space imagery, and it's honestly worth trying out for yourself. There's also a fascinating computing challenge behind all of this that rarely gets discussed. Producing 20 terabytes of raw data every single night for 10 straight years makes this one of the largest ongoing data engineering efforts in modern science. Specialized processing centers calibrate incoming images, remove instrumental noise, compare each new image against a constantly growing reference library of that same patch of sky and flag meaningful changes automatically, all within minutes, night after night, without any realistic way for humans to review each image in real time. Machine learning systems handle the flood, learning to distinguish a genuinely new event from routine noise or a simple glitch. Without automation at this scale, the sheer volume of information this observatory produces would be impossible for any team to keep up with manually. It's also worth pointing out how democratized this data is expected to become over time. Unlike past major astronomical projects, where raw data stayed restricted to a small circle of researchers for years, this survey was designed with broader access in mind from the start. After certain proprietary periods for the core science teams, much of this data becomes available to the wider global research community, and eventually the public, meaning students and dedicated amateur astronomers, may get to work directly with observations from one of the most powerful telescopes ever built. That kind of open access could meaningfully accelerate discoveries beyond what any single research team could accomplish alone, simply by putting an enormous data set in front of far more curious eyes across the planet. Consider how much of the sky remains genuinely unexplored at this level of detail and repetition. Previous major surveys have given astronomers snapshots, single, moments frozen in time across large sections of sky. What makes this project fundamentally different is repetition. By returning to the same patches of sky roughly every 3 to 4 nights across a full decade, this observatory isn't just building a static map of the universe, it's building something much closer to a movie, capturing how individual stars flicker, how galaxies suddenly shift and interact with one another, and how objects within our own solar system move against the backdrop of deep space over time. Many of the most interesting astronomical events, a star suddenly exploding as a supernova, an asteroid swinging unexpectedly close to Earth, a distant galaxy briefly flaring as material falls into its black hole, are inherently temporary. Without a system built to watch the same regions of sky again and again, many fleeting events would simply go unnoticed, hidden between the gaps of less frequent observation. That's really the heart of why this project matters so much. Beyond the impressive hardware and record-breaking pixel counts, it's not simply about taking prettier pictures than what's come before, although these images are genuinely stunning in their own right. It's about fundamentally changing how frequently and how completely we watch the sky, turning occasional glimpses into something closer to continuous observation across half the visible universe as seen from Earth. Based on what's already emerged from just 10 hours of early test observations, thousands of newly discovered asteroids, tens of millions of newly catalogued galaxies, dozens of previously unknown pulsating stars, and 2 entirely new mosaic images that instantly became some of the most detailed astronomical photographs ever released. It's genuinely difficult to overstate how much more is likely coming once the full 10-year survey runs at complete operational capacity. If a project like this excites you the way it excites me, subscribe right now, because we'll be covering every major discovery that comes out of this observatory as the data starts rolling in over the coming years. And trust me, you will not want to miss what gets found.